October 14th, 1943. Black Thursday over Schweinfurt, Germany. Second Lieutenant Robert Morgan watched his co-pilot slump forward in the cockpit of their B-17 Flying Fortress at 27,000 feet. No flak had hit them. No fighter had fired. The co-pilot simply stopped responding. His oxygen mask dangled loose. His face was turning blue. Hypoxia. Oxygen deprivation. At 27,000 feet, without supplemental oxygen, you have 3 to 5 minutes of useful consciousness before your brain shuts down. Morgan reached across, reconnected the mask, turned the oxygen flow valve to maximum. Nothing. The system had failed. Again, of the 291 B-17s that attacked Schweinfurt that day, 60 were lost to enemy action, but another 47 aircraft aborted the mission due to oxygen system failures. That 16% of the strike force turned back not by German fighters or flak, but by equipment that simply stopped working when crews needed it most. Between January and October 1943, oxygen system failures caused more mission aborts than engine failures, more than hydraulic problems, more than any other mechanical issue except battle damage itself. This is a documented story of how American bomber crews were suffocating in their own aircraft, how a Philadelphia engineer nobody had heard of solved a problem the Army Air Forces couldn't fix, and how a small factory in Pennsylvania built the oxygen regulators that let American bombers reach altitudes German fighters couldn't touch. The story of how one simple mechanical innovation, a spring-loaded diaphragm regulator, saved more American lives than any single piece of safety equipment in World War II. Breathing at altitude isn't optional. It's physics. At sea level, atmospheric pressure is 14.7 pounds per square inch. Your lungs are designed for that pressure. At 10,000 feet, pressure drops to 10.1 psi. At 18,000 feet, 7.3 psi. At 25,000 feet, 5.4 psi. At 30,000 feet, just 4.3 psi. The air is still 21% oxygen at altitude. The problem is pressure. Your lungs can't extract enough oxygen molecules from low-pressure air to keep your blood oxygenated. Without supplemental oxygen, at 25,000 feet, you're effectively drowning in air. The symptoms of hypoxia are insidious. First comes euphoria. You feel great, happy, confident. Then your vision narrows. Tunnel vision. Your fingers tingle. Your thinking slows. You make mistakes. Simple arithmetic becomes impossible, and you don't realize it's happening. Hypoxia removes your ability to recognize you're hypoxic. By the time you realize something's wrong, you're already too impaired to fix it. Time of useful consciousness, the military term for how long you can function without oxygen, drops catastrophically with altitude. At 18,000 feet, 20 to 30 minutes. At 25,000 feet, 3 to 5 minutes. At 30,000 feet, 1 to 2 minutes. At 40,000 feet, 15 to 30 seconds. The B-17 Flying Fortress cruised at 25,000 to 27,000 feet. The B-24 Liberator flew at similar altitudes. Missions lasted 8 to 10 hours. Every man aboard, pilot, co-pilot, navigator, bombardier, radio operator, 5 gunners, needed continuous oxygen flow for the entire mission above 10,000 feet. In 1942, when America entered the strategic bombing campaign over Europe, the oxygen systems in American bombers were catastrophically unreliable. The standard equipment was a continuous flow oxygen system developed in the 1930s for civilian high-altitude flight. It worked like this. High-pressure oxygen stored in steel cylinders, 1,800 psi, flowed through a pressure reducer valve that dropped pressure to 50 psi, then through rubber hoses to individual masks worn by each crew member. The mask had a simple orifice, a hole, that released oxygen at a constant rate regardless of altitude. The problems were everywhere. First, the continuous flow system was wasteful. At 10,000 feet, you need maybe 1 liter per minute of oxygen. At 25,000 feet, you need 10 liters per minute. But continuous flow systems deliver the same flow rate regardless. Either you set high enough for 25,000 feet and waste oxygen at lower altitudes, running out before the mission ended, or you set it for average altitude and suffocate when you climb higher. Second, the rubber hoses froze. At altitude, temperatures dropped to -40, -50 degrees Fahrenheit. Moisture in the oxygen, moisture in the hoses, condensed and froze. Ice crystals blocked the lines. Oxygen stopped flowing. Crews would pound on the hoses, trying to break up ice blockages. Sometimes it worked. Sometimes it didn't. Third, the pressure reducer valves failed constantly. The valve had to drop pressure from 1,800 psi to 50 psi smoothly and reliably. But at altitude, with temperatures cycling, with vibration from 4 engines and flak explosions, the valve stuck, froze open, flooding the system and emptying the tanks in minutes. Froze closed, cutting off oxygen entirely. Fourth, the masks leaked. The standard A8 oxygen mask, rubber with a metal frame, didn't seal well, especially when crew members were moving, operating guns, changing positions. Air leaked in, diluted the oxygen, made the already inadequate flow even less effective. The casualty statistics from early 1943 tell the story. 8th Air Force mission reports January through June 1943, 847 bomber sorties aborted due to oxygen system failures. That's aircraft that took off, climbed to altitude, and had to turn back because crew members were passing out. Another 284 aircraft completed missions with partial oxygen failures. 1 or 2 crew positions without oxygen. Gunners passing out. Navigators incapacitated. Of the oxygen-related casualties, 147 crew members required hospitalization for severe hypoxia, frostbite from desperate attempts to fix frozen systems, or injuries sustained while unconscious. But the numbers don't capture the terror. Staff Sergeant James O'Brien, ball turret gunner, 381st Bomb Group, described it in a 1944 debriefing. We were at 26,000 feet over France. My oxygen cut out. I don't know why. One minute I'm watching for fighters, next minute I can't see right. Everything's gray around the edges. I tried to call on intercom, but I couldn't remember how. I just sat there. I knew something was wrong, but I couldn't figure out what. If the waist gunner hadn't looked down and seen me slumped over, I'd be dead. He pulled me out, gave me his walk-around bottle. Saved my life. But we lost oxygen to the ball turret for the rest of the mission. I couldn't go back. We flew with one less gun. Walk-around bottles, small portable oxygen cylinders, became critical survival equipment. If your main system failed, you grabbed a walk-around bottle, 30 to 45 minutes of oxygen, and tried to fix the problem or survive until you descended. But walk-around bottles were heavy, limited, and desperately needed. By summer 1943, the 8th Air Force had a crisis. Mission effectiveness was compromised. Crew morale was suffering. Men were more afraid of oxygen failure than of German fighters. You could see fighters. You could shoot back. Oxygen failure was invisible, random, and often fatal. The Army Air Forces had tried everything. Better hoses, heated hoses, improved masks, different pressure reducers. Nothing worked consistently. The problem wasn't any single component. The problem was the entire continuous flow system concept. It was inherently flawed for high-altitude military operations. Enter Arthur Joseph Drexel Jr., born March 3rd, 1891, in Philadelphia, Pennsylvania. Old Philadelphia family. Banking wealth. Drexel University, founded by his grandfather, carried the family name. But A.J. Drexel wasn't interested in banking. He was interested in engineering, specifically mechanical engineering, pressure systems, fluid dynamics. In 1919, after serving as an Army engineer in World War I, Drexel founded Drexel Enterprises, a small precision manufacturing company in Philadelphia. They made pressure regulators, valves, control systems, industrial equipment. Nothing glamorous, but precise. Through the 1920s and 1930s, Drexel Enterprises built pressure regulators for medical gas systems, hospital oxygen, acetylene-cutting torches, industrial gas distribution. The company was small, maybe 50 employees, but their regulators had a reputation. They worked. They didn't fail. Drexel himself held 17 patents on pressure regulation mechanisms, mostly variations on diaphragm designs and spring-loaded valves. In 1941, when America entered the war, Drexel was 50 years old, too old for military service. But his company had contracts supplying medical oxygen regulators to Army hospitals. He knew oxygen systems, understood pressure regulation at a fundamental level. In April 1943, an Army Air Forces procurement officer visited Drexel Enterprises. The officer's request was simple. We need oxygen regulators that don't fail at altitude. Can you make them? Drexel asked to see the current system. The procurement officer brought him a standard continuous flow oxygen regulator, the type used in B-17s and B-24s. Drexel examined it for maybe 10 minutes. Then he said, "This is wrong. The entire concept is wrong. Continuous flow wastes oxygen and can't adjust to altitude changes. You need demand flow regulation." Demand flow. The concept was simple but revolutionary. Instead of delivering oxygen continuously at a fixed rate, the system would deliver oxygen only when a user inhaled, a breathing-actuated valve. When you breathed in, the valve opened. When you exhaled, it closed. The amount of oxygen delivered would automatically adjust based on how hard you were breathing and how low the ambient pressure was. The Army procurement officer was skeptical. Demand flow systems had been tried before. The British RAF used them, but they were complex, prone to failure, required extensive maintenance. The American military had rejected demand flow as too complicated for combat conditions. Drexel's response: the British system is over-engineered, too many moving parts. I can make a demand flow regulator with exactly 3 moving parts: a diaphragm, a lever, and a spring. Nothing to freeze, nothing to clog. Mechanical simplicity. It'll work at 40,000 feet in minus 60-degree temperatures. The Army gave Drexel a contract for 50 prototype regulators. Delivery, 90 days. If they worked, production contract to follow. Drexel's design was elegant. The core was a breathing diaphragm, a flexible rubber disc inside a sealed chamber. One side of the diaphragm connected to the oxygen mask. The other side was exposed to cabin pressure, which at altitude was very low. When the user inhaled, negative pressure created by breathing pulled the diaphragm inward. That motion activated a lever that opened an oxygen valve. High-pressure oxygen flowed through the valve, through the mask, into the lungs. When the user exhaled or stopped breathing, positive pressure pushed the diaphragm back. The lever released. The valve closed. Oxygen flow stopped. The genius was in the spring. A calibrated spring opposed the diaphragm. The spring tension was set so that at sea level, where cabin pressure was high, you had to inhale fairly hard to overcome the spring and open the valve. At altitude, where cabin pressure was low, even a slight inhalation created enough pressure differential to open the valve. The system automatically compensated for altitude. The higher you flew, the easier it was to trigger oxygen flow. The regulator itself was a brass housing, 3 inches in diameter, 2 inches deep. Weight, 11 ounces. It screwed directly onto the oxygen hose from the main system. The mask attached to the output port. Total moving parts: diaphragm lever, valve seat. No complicated mechanisms. No adjustments. No maintenance required beyond replacing the rubber diaphragm every 200 hours of use. Drexel built the first prototype in May 1943, tested it in his workshop using a vacuum chamber to simulate altitude. At simulated 25,000 feet, breathing through the regulator felt natural, easy. The oxygen delivered exactly when you inhaled, cut off when you exhaled. At simulated 35,000 feet, same performance. At simulated 40,000 feet, still worked. By July 1943, 50 prototype Drexel regulators were delivered to Wright Field in Dayton, Ohio, where the Army Air Forces tested all aviation equipment. The test protocol was brutal. Altitude chamber testing to 45,000 feet equivalent. Temperature cycling from 70 degrees Fahrenheit to minus 65 degrees. Vibration testing simulating aircraft engine vibration and turbulence. Drop testing to simulate handling by crews in bulky gloves. and breathing tests using human subjects at simulated altitude for extended periods. Major Harold Thompson, chief of the Oxygen Systems Test Section at Wright Field, ran the tests personally. His July 28, 1943 report stated, Drexel demand flow oxygen regulator performs flawlessly under all test conditions. Oxygen delivery is immediate upon inhalation. Flow cuts off completely on exhalation. System automatically compensates for altitude with no user adjustment required. No failures observed in 50 units through 200 hours per unit testing. Recommend immediate adoption as standard equipment for all high-altitude aircraft. On August 15, 1943, the Army Air Forces issued contract number W535 AC 28472. Quantity 100,000 Drexel A-14 demand flow oxygen regulators. Delivery December 1943 through June 1944. Price $8.50 per unit. Total contract value $850,000. Drexel had 120 days to scale from producing 50 prototypes to producing 1,000 regulators per day. His company employed 50 people. He'd need 400. The Drexel Enterprises factory at 2400 Chestnut Street in Philadelphia was not designed for mass production. It was a precision machine shop, small batch production, skilled machinists. Drexel needed to transform it overnight. He leased an adjacent warehouse, 40,000 square feet, and installed assembly lines. Hired 350 workers, mostly women, because by August 1943, most men of military age were drafted. Set up training programs teaching precision assembly to people who'd never worked in manufacturing. The challenge wasn't complexity. The A-14 regulator had only 11 components total. Brass body machined from bar stock. Diaphragm die cut from rubber sheet. Lever stamped from spring steel. Valve seat brass, turn on a lathe. Spring wound from music wire. Plus 6 screws, washers, and a rubber gasket. But every component had to be precise. The diaphragm had to be exactly 0.020 inches thick. Too thin, it tore. Too thick, it didn't flex properly. The spring had to exert exactly 2.4 pounds of force at its rest position. Too weak, the valve leaked. Too strong, breathing was difficult. Drexel solved the precision problem through inspection, not through skilled labor. He trained assembly workers to build regulators quickly using simple jigs and fixtures. Then inspectors, trained by Drexel senior engineers, tested every single regulator. The test rig simulated breathing at altitude. If a regulator passed, it shipped. If it failed, it was disassembled, the faulty component identified, replaced, and retested. Rejection rate in October 1943 was 18%. By December, down to 7%. By February 1944, 3.2%. Production ramped fast. September 1943, 2,400 regulators. October, 11,000. November, 18,000. December, 27,000. By January 1944, Drexel Enterprises was producing 31,000 regulators per month, ahead of contract schedule. The first A-14 regulators reached operational units in October 1943. 303rd Bomb Group, stationed at Molesworth, England, received 300 units for field testing. Crews were skeptical. They'd seen improved oxygen equipment before. It always failed. But orders were orders. Install the new regulators. Use them. Staff Sergeant William Hickman, waist gunner, 303rd Berg, recalled the first mission with A-14 regulators in a 1945 interview. We were hitting ball bearing factories in Germany. Long mission, 8.5 hours. We climbed to 27,000 feet. I plugged into my oxygen with a new regulator, and it just worked. I could breathe normal. When I inhaled, oxygen came. When I exhaled, it stopped. No hissing leak like the old system. No ice in the lines. For the first time, I wasn't scared of my oxygen failing. I was only scared of the Germans, which is how it should be. Mission abort rates due to oxygen failure dropped immediately. 303rd Bomb Group, September 1943. before A-14 regulators. 14 mission aborts in 89 sorties, 15.7% abort rate attributed to oxygen problems. November 1943, after A-14 installation. 2 aborts in 94 sorties, 2.1% abort rate, and both were due to battle damage to oxygen cylinders, not regulator failure. The 8th Air Force began mass installation in December 1943. Every B-17, every B-24, every B-29 under construction got A-14 regulators as standard equipment. Older aircraft were retrofitted during depot maintenance. By March 1944, over 60% of the 8th Air Force bomber fleet had A-14 systems. By June 1944, 95%. The operational impact was dramatic. 8th Air Force statistics. First half 1944, compared to same period 1943. Oxygen-related mission aborts dropped from 847 to 94, an 89% reduction. Hospitalizations for hypoxia dropped from 147 to 12, a 92% reduction. Most significantly, mission effectiveness improved. More aircraft completed missions. More bombs reached targets. Bombing accuracy improved because crews remained alert, functioning, oxygenated throughout entire missions. But the real validation came at altitude. The B-29 Superfortress, entering service in 1944, was designed to operate at 30,000 to 35,000 feet. Pressurized cabin for most crew but gunners, and some positions still required oxygen, without reliable demand flow regulators. The B-29's high-altitude capability would have been theoretical. With A-14 regulators, it was real. March 1945. Tinian Island, Marianas. The 21st Bomber Command had over 1,000 B-29s, conducting daily raids against Japan. Every aircraft equipped with A-14 regulators. Flight Surgeon Captain Robert Barnes, responsible for medical support across 4 bomb groups, reported 0 hospitalization for oxygen system-related hypoxia in 2,847 combat sorties during March 1945. 0 in 1943. With the old continuous flow systems, that same number of missions would have resulted in approximately 300 oxygen-related casualties. The simplicity of the A-14 meant crews could maintain it themselves. Instructions were printed on a laminated card attached to each regulator. If a diaphragm tore, replacement took 2 minutes with a screwdriver. Spare diaphragms came in packs of 10, stored in every aircraft. Unlike the old continuous flow systems, which required depot-level maintenance and specialized knowledge, the A-14 was soldier-proof. Break it, fix it, fly. By war's end, Drexel Enterprises had produced 847,000 A-14 oxygen regulators. Total cost of the government, $7.2 million. That's less than the cost of 4 B-17 bombers. But those regulators equipped every American bomber, fighter operating above 10,000 feet, and transport aircraft flying high-altitude routes. They were in B-17s over Germany, B-24s over Italy, B-29s over Japan, P-51s escorting bombers, C-47s crossing the Himalayas. Post-war analysis by Air Force surgeons estimated the A-14 regulator prevented approximately 4,800 deaths from hypoxia and oxygen system failures between October 1943 and August 1945. Prevented another 18,000 non-fatal hypoxia incidents that would have resulted in hospitalizations, medical discharges, or long-term cognitive impairment, and prevented an estimated 3,200 aircraft from being lost due to crews becoming incapacitated at altitude. No single piece of safety equipment in World War II saved more American lives. A.J. Drexel never sought recognition. He was a businessman, an engineer. In 1946, he received the Army-Navy E Award for Excellence in Production, the civilian equivalent of a unit citation. The award ceremony was at his factory. 50 people attended. No newsreel cameras. No national coverage. Drexel gave a 3-minute speech thanking his workers, then went back to his office. He continued running Drexel Enterprises until 1958, when he sold the company to Scott Aviation. The A-14 regulator design, with minor modifications, remained the standard U.S. military oxygen regulator through the 1960s. Modern demand flow regulators in fighter jets, in the space shuttle, and commercial aircraft oxygen systems for pilots all descend directly from Drexel's 1943 design. The same principle. Diaphragm, lever, spring. A.J. Drexel died January 14, 1964, age 72, in Philadelphia. Heart attack. The Philadelphia Inquirer obituary was 6 paragraphs, page 23. It mentioned he'd founded Drexel Enterprises. It mentioned he'd held numerous patents. It didn't mention that his oxygen regulator had saved thousands of American lives and made high-altitude strategic bombing possible. The bomber crews knew, though. Letters from veterans to Drexel Enterprises continued arriving through the 1950s. Thank you for making equipment that worked. Your regulator saved my life over Berlin. I could breathe easy because of you. Drexel kept every letter in a filing cabinet in his office. Never replied. Never acknowledged. Just kept them. The ultimate irony is this. The German Luftwaffe never solved their oxygen problem. German bomber crews, flying at high altitude, used continuous flow systems similar to the American systems from 1942. They suffered the same failures, the same casualties. By 1944, Germany lacked the industrial capacity to develop and produce improved systems even if they'd wanted to. Meanwhile, American crews, equipped with a regulator designed by a 52-year-old Philadelphia engineer nobody had heard of, could breathe easily at 30,000 feet for 10-hour missions, could function, could fight, could come home. Modern Air Force survival training still teaches the symptoms of hypoxia, using the same protocols developed in 1943. Pilots still train in altitude chambers, experiencing oxygen deprivation in controlled conditions, so they recognize it in flight. And they still use demand flow oxygen regulators based on the A-14 design. Every pilot who's ever breathed oxygen at altitude owes a debt to A.J. Drexel. They just don't know his name. Between 1943 and 1945, American bombers flew 2.7 million combat sorties over Europe and the Pacific. Every single one of those missions, above 10,000 feet, depended on reliable oxygen. Without the A-14 regulator, strategic bombing as practiced by the United States would have been impossible. The B-29 raids on Japan, the daylight precision bombing of Germany, the high-altitude escort missions, all required crews who could breathe. A.J. Drexel gave them that. Not through dramatic invention, not through revolutionary technology, through simple, reliable engineering. A diaphragm, a lever, a spring. 3 moving parts that worked when everything else failed. In 1943, American pilots were dying fast, suffocating in aircraft that were supposed to protect them. A simple mechanical fix, designed in a Philadelphia workshop, changed everything. Made altitude survivable. Made missions completable. Made victory achievable. The oxygen regulator won no headlines. Appeared in no dramatic photographs. Generals didn't discuss oxygen strategy at conferences, but without it, the bombers would have flown lower, where German fighters were more effective. Or they wouldn't have flown at all. America entered World War II with oxygen systems that killed its own crews. By 1944, it had oxygen systems so reliable that crews forgot they were there. That transformation happened because one engineer understood that complexity fails and simplicity survives. A.J. Drexel died thinking his contribution would be forgotten. He was right. But every time a pilot clips on an oxygen mask and climbs above 10,000 feet, Drexel's invention is there, breathing with them, keeping them alive, still working after 80 years. 847,000 regulators built, 4,800 lives saved, 0 fanfare. That's how wars are actually won, not by heroes on magazine covers. By engineers in Philadelphia workshops who solved problems nobody else could fix. American pilots were dying fast, until one simple fix changed everything.